Hello guys and welcome back to my channel Interview with Bunny. So in our last video we have seen a new topic on graph, and that is the topological sort, where we have seen in detail that what is a topological sort, what is a real life use case of a topological sort, and in our last video we have tried to understand the algorithm of the topological sort with this two example. I hope you have gone through my previous video, otherwise this video is completely useless, because without understanding that what is a topological sort, why we are using a DAG over here and all the concept, it is meaningless to proceed further. So with the assumption that you have gone through my previous video, let's start with this video, and here we will see how to derive these two topological sort with the help of the DFS algorithm. So let's proceed and let's see how to implement the topological sort using the DFS approach. And believe me, it is very easy. And as usual, I will explain you the entire algorithm from scratch, and it will be very easy for you to understand. So let's proceed further. So here, to implement the topological sort using the DFS approach, you need an additional data structure, that is stack. So let's start with defining a stack over here. And as usual, you know that a DFS need a visited array or a visited set. So we will define a visited set over here. So we will call a visited set over here. So at the very beginning, it is empty. Now we will start with our DFS traversal from the node 0. So let's start our DFS traversal from node 0. Since we have started our DFS traversal from node 0, as per the rule of DFS, what we will do, we will mark the node as visited. So we will mark it as visited. Now what we'll do, we will check what are the neighboring nodes or what are the edges where it is directing from the node 0, which is nothing but node 1 and node 2. So we will start with the first node, and that is the node 1. So from the node 0, we will call our next DFS call, and that is node 1. So we are right now at node 1 over here, and we will mark it as visited. Now again, what we'll do, from node 1, we will again call the DFS, and here you can see the neighboring nodes are node 3 and node 4, where it is heading towards. So here we will choose the node 3 for example. So we'll make the another call, that is DFS of 3, and we will mark it as visited. And from node 3, we will make another call, and that is the last and the final DFS call over here for node 3, and that is DFS of 5. And we will mark it as visited. That's it. We are done coming to the node 5, and that is the last node for this path. Now comes the main thing. Here if you look carefully at node 5, there is no neighboring nodes or there is no edges from where we can travel forward. So this is the last node or the last vertex for our traversal. So what we have to do, according to the base condition of the DFS traversal, what we have to do, we have to return from here. But here, before returning, what we have to do, we have to insert that value into the stack. Since it's the last element of the traversal and no further traversal is possible, so we will return from here and we will put this value in the stack. So node 5 will go into our stack. Understand? Now why we are putting in the stack and what is the intuition and logic behind that? Just wait for a minute, I will explain you clearly why we are doing so. But right now just understand this algorithm. So now what we have to do, we are now at node 3. So we are standing over here. And again from node 3, according to DFS, we will see whether there is any unvisited neighboring nodes or not. And here you can see there are no unvisited node over here. So what we will do, we'll again backtrack. So we will return from node 3, and before returning from node 3, we will push the value in the stack. So we will push it over here. That is node 3 comes over here. So right now where we are at node 1, that is over here. Now at node 1, we will again check that what is the other neighboring node that are unvisited. And here you can see other neighboring node that is unvisited, that is node 4. So what we'll do, we will make the DFS call from node 1 to node 4. So here we will make the call as DFS of 4 and we will mark it as visited. Done. Now again from node 4, what we'll do, again we will make a DFS call and we'll check what are the neighboring node. But here in this case, since node 5 is already marked as visited, so you know we do not have to proceed further with the DFS traversal. So our iteration ends over here and we will return back from here. So from node 4, we will again return back to node 1. And before returning back, what we have to do, we have to simply print the value or push the value in the stack. So we are right now at node 1 again. Now from the node 1, do we have any other unvisited node to traverse? It is not possible because all the neighboring nodes are visited. So what we'll do? We will backtrack to node 0. So from node 1, we will backtrack to node 0, and what we'll do? We will push the node 1 into the stack. So we are done. We are right now at node 0. Now what we'll do? We will make another DFS call to the unvisited node of node 0, and that is we will make the call to DFS of 2. So let's go to this way right now. So here we have made the call to DFS of 2 and we will mark it as visited, and that's it. Now what we'll do, again from node 2, we will check what are the neighboring nodes, and here you can see we have the neighboring nodes, that is node 3, but it is already marked as visited. So we will simply skip it, and since there are no other nodes that we can travel from node 2, we will simply return from here. And while returning, what we'll do, we will simply push the value in the stack. And that's it. We are again at the first node, that is the node 0 from where we have started. So from here we'll check whether there is any neighboring nodes that are pending or not. And here you can see there is no neighboring nodes that are pending to traverse. And so what will happen? We will return back from here to the calling function, but before returning back, and we will push the value in the stack. And that's it. We are completely done with the DFS traversal for this graph. Clear? So have I done anything extra? Nothing, right? It is a simple DFS traversal, but just before returning back, we are just inserting the value in the stack. That is the only extra step that we have done within the DFS traversal. Now, if you just look at the value of the stack carefully, you will see we have already got our answer. So let's print the stack over here. So let's print the value of the stack over here. So the first element that will come out from the stack is node 0, followed by node 2, then 1, then 4, then 3, and then 5. So if we print all the values of the stack, you can see we have got our answer, that is the topological sort answer that we have seen over here. This is the same answer that we have seen before. So here you can see how easily, with the help of this algorithm, that is the simple DFS logic, we have found out the topological sort for this graph. I think this is clear that how this algorithm is working. Now I know you have lots of questions in mind, that is how come we can get this result, or what about the other result that are possible. Let me answer all the questions that comes to your mind. So here if you look carefully, once we were traversing from node 0, what we have done, we have traversed to the node 1 first, rather than taking the path node 2. Here in the alternative approach, if you start with the node 2 rather than node 1, you can see you will get this answer, because here you can see you are first going from node 0 to node 2 and then you are going to node 1 and all this case. So as you know, since the DFS is a recursion technique, and here you have lots of possibilities to traverse. So whatever the possibility you have and whatever the path you take, it will produce one answer, and that answer will be one of the topological sort of your algorithm. I hope this is clear that why a topological sort can have multiple answers for a same problem. That is because we have multiple options or multiple recursion paths to follow during the DFS traversal. I hope this is clear now. Now the question is why we are actually using a stack over here, and what is the actual fundamental algorithm or concept by which we are driving this algorithm. So let me tell you what we are doing. So if you have remembered, in our last video, we have taken an example of some process and the task running in our computer. And the example was something like this. So here we have 5 tasks running for a single process. And if you remember the topological sort of this one, it was something like this. So these are again the 2 topological sort that can be done out of all the 4 or 5 topological answers that are possible. So let's see how the things are happening over here, and let's understand the real life intuition that why we are performing the algorithm in this way. So what we are doing, we are actually using a stack over here. And if you know, these are some running tasks that are running in our computer. And your task T2 cannot start until and unless T1 ends, right? Similarly, your task T3 cannot start until and unless T1 ends. So this T2 and the T3 are some dependent tasks of T1. Now, if you look carefully, these T2 and T3 are the last task of our process, and there are no other further dependent task of T2 and T3. Means from T2 and T3, there are no other tasks like T6 or T7. So here T2 and the T3 are the last terminating task for our process. So our main intuition is we have to find out the last task of our process, after which there are no further tasks that are possible. And here if you see, T2 and T3 are those type of tasks, means from there no further task can be possible. Now if you implement the DFS algorithm over here, you will see we are starting our DFS traversal from DFS of 1, means from here. And from here what we are doing, we are again making the DFS call to its neighboring nodes, which is nothing but DFS of 2. Now here if you see, task 2 is the last task that got completed, and there are no further tasks that are possible. So task T2 is the last atomic task for this entire process. So what we have to do, since there is no dependence task on T2, we have to just list down T2 over here. So what we are doing, before returning from T2, we are just pushing it into the stack. Means we are confirming that whatever the things we are pushing in the stacks, that is the last task that can be performed, and no other further task can be processed from there. So here for this example, T2 is the last task that can be performed. Now, if we go back and make the return from the DFS call, you will see we will go to the DFS of 1, that is over here. Now we will make another DFS call to the node 3, which is nothing but DFS of 3. And here you can see also 3 is the last node or the last task for this process. So what we will do, so since this is the terminating task and no further task can propagate from task 3, that's why we are pushing it in the stack, and we are confirming that from T3 no other task can be done. Now what will happen? We will again go back or return from T3. We are at task 1, that is node 1. And here in node 1, if you see, at node 1, both the tasks T2 and T3 are already completed and already are in the stack. Means T1 is already independent right now, because there are no other tasks that are dependent on T1, because all the child tasks are already done. So he is free right now, means T1 is free. And since T1 is completely free right now, what we will do, we will push it in the stack. So right now T1 goes over here. That's the main concept. So what we are doing, whatever the things that are pushing in the stack, we are just confirming that there are no further DFS call or there are no further tasks that can be possible from that respective task. That is the main intuition why we are using a stack and why we are doing the algorithm in this way. Now, similarly, what we'll do the same thing for T4. So here you can see we will start the DFS from T4, that is DFS of 4. And here we will make the another call, that is DFS of 5. And at DFS of 5, you can see this is the last node. And since there is no other dependent task on task 5, we will push it in our stack. So T5 goes over here. And once T5 is completed, we will return back from T5. And we are right now at T4. And here, since T5 is already done, means T4 is independent, means there is no dependent task on T4. So we will again push that T4 into our stack, and thus T4 go inside our stack. And thus if we just print the value of the stack, you will see T4, T5, T1, T3 and T2. This will become our topological sort for this graph, and this is a valid topological sort. I hope this is clear that how we are doing the topological sort or how we are implementing the topological sort with the help of the DFS approach. And remember this concept clearly, that whenever a task gets independent, means there are no further tasks that are possible from a particular task. We are telling that this task is independent and this can go in the stack. Because with this concept in mind, we will learn the Khan's algorithm or the Khan's algorithm in our next video. So I will request you right now, with this concept in mind, just go back and just see the video one more time so that the algorithm will be damn clear to you and you will understand that how the things are working over over here. Now, how we will code it in Java? That is a simple few lines of code that will hardly take 2 to 3 minutes for you to understand. So let's start with implementing this algorithm with the Java code, and let's see how to implement the topological sort with the help of the DFS traversal. So let's start coding. So here you can see we are back with our online compiler over here, and let's now go through the code and let's see how easy it is to implement the topological sort using the DFS technique. So here you can see this is our main block, and as usual we are using the same pattern of coding that we are doing for the last 13 videos. So here we have our graph class, which is nothing but the same implementation over here. So this is our graph class, and here this is our main class. So what we are doing, we are simply creating an object called as graph, and here we have implemented the same graph that we were discussing right now. So our graph object is right now created. Now what we are doing, we are calling the function called as topological sort. So let's see what is there within the topological sort function. So here if you look carefully, this is our topological sort function. And here if you look carefully, we are doing nothing special. What we are doing, we have simply declared a visitor set over here, which is nothing but the same thing that we do for a DFS call. Here only thing that we have done extra is like here we have declared another data structure called a stack. I hope right now you are clear why we need this additional data structure over here. Now here what we are doing, here we are just doing the same thing that we do for the DFS traversal. That is, we are iterating over each and every nodes over here, and we are checking that whether the nodes are visited or not, and if the node are not visited, then we are making the DFS call over here. And if it is visited, means we have to simply skip it, and we have to keep on iterating over all the nodes of the graph. That is a simple thing that we are doing over here. Now let's see the main and the important block of code, and that is this DFS traversal. Now here if I expand this DFS traversal, you can see this is only just the 5 lines of code by which you can simply implement the topological sort using the DFS technique. And what we are doing nothing extra. We have just added one line of code, that is this line. So what we are doing here, just the way we do our DFS traversal, we are first inserting the value in our visited set, means our vertex got visited. Now for that vertex, we are iterating over all its neighboring nodes, and we are recursively calling our functions over here. And once the recursion ends, means there are no further neighboring node possible. At that time, what we are doing, we are simply pushing the value or pushing the vertex in the stack. And that's it. That is the only thing, that is the only modification that you have to do in your DFS algorithm to implement the topological sort. And at the very last, in the topological sort function, we are simply printing this stack over here, and that's it. So let's now run this code and let's see whether we are getting the answer or not. So if I click on run, and great, here you can see we are getting the topological sort, that is 021435. And that's it. Here, this is your answer for the topological sort. So I hope you have thoroughly understood this video and you have found this video useful. And if you have found this video useful, do not forget to like, share and subscribe to my channel and hit the bell icon so that you never miss an update from my channel and you are always ready for your next interview. So let's see you on our next video where we will learn an important algorithm, and from that algorithm we can simply prove two things, that is finding the topological sort with the help of the DFS algorithm, and we can also find out the cycle detection for a directed graph using the DFS approach. So see you on our next video where we will be solving the topological sort algorithm with the help of the Khan's algorithm. So see you on our next video. Thank you.